In this video and notebook, we're going to look at outlier detection, which is a very difficult task. It's one of the harder parts of pre-processing a data set, and for several reasons. The first thing is that it's a rather vague idea. You want to identify the data items which do not follow the dominant pattern. But, the data set is enormous, it's noisy, it's structured in some complicated way, perhaps. And there's a chicken and egg problem. Your whole data set has outliers. But what you really want is a sense of what the data should look like without outliers so that you can understand the relationships and then understand what the outliers are. But the outliers are in it, and they affect your view of what the relationships are. So there's a little bit of circularity there, and it makes it difficult. There's just a lot of different ways to do this. So we're going to look at, in this notebook, we're going to look at a couple of different methods, 5 different methods, essentially. 3 for the univariate case, and then 2 for the multivariate, which of course are more interesting for data scientists. One of them just being what's called coordinate-wise, just applying the univariable case component-wise. And then we'll look at the gold standard, which is the Mahalanobis distance. And that's probably the best thing you can use, but all of these have their role. Okay, let's look at the one-dimensional case. First of all, you can always just, I didn't even go very far with this absolute deviation. You can always say, well, let me find the mean, calculate the deviation from the mean. It's a distance, so it's an absolute value. And just, if it's over some t, some fixed boundary, it's an outlier. That might be suitable in some special cases, but it's pretty limited. Something you might have some intuition about is the z-score method. It's used, throughout statistics, introductory statistics. You standardize, you get the z-score, take each value, univariate, and subtract the mean, divide by the standard deviation. This is pretty much intended for things that are normally distributed. It won't work as well with things that are not normally distributed. We'll see in a moment. But in any case, you do this, then the absolute value of z is the number of standard deviations away from the mean. Typical values, you pick 2 or 3, eliminating more and more of the values that are too far away from the mean. So the decision boundary is shaped like this. It's this is two-sided because of the absolute value, but you just need one side. So you have that typical half of the normal distribution curve to provide the decision boundary. And it doesn't work all that well. Let's look at an example. It works well when it's normally distributed, but it's not normally distributed. Not so well. Here's a very non-normally distributed. 1, 2, 3, 4, 5. It was supposed to be 6, 7, but when they entered it, they got 67. They left out a comma. You end up with 67 way out here. Obviously, just look at this, it's crazy. The problem is, when you actually calculate it, here's 2 standard deviations. You only have to look on the positive side. Here's 3. If your rule is 3 standard deviations, it's not an outlier, which is ridiculous. If you use 2, well, then it's fine, but now you're letting in perhaps a lot of other things. So it doesn't work very well. Why not? Because the mean is not very stable. Look, this outlier pulled the mean to the right. The mean is larger than any number here. And then everything shifts. So it's not very stable. Now, this is a standard situation in statistics, and what you do is you use a median instead. And it's more difficult to work with, but it gives you better results. So the median, talked about how to calculate that. You calculate the median of the data set, and then you essentially replace the median everywhere the mean would have been before. So you have the median, and when you normalize, you're going to subtract the median. You also have the analog of the standard deviation. Instead of the average of the squared deviations, in this case, it's using like an L1 kind of metric. It's the median of the absolute values, not squared. And then you use it like a standard deviation, and then you use it the same. You say the same thing. You're going to cut off after 2 mads or 3 mads or whatever. Okay, here's some of the details. But notice, why that median is stable. If this were a 6, just a 6, this would stay the same. If it was 67 billion, it would still be 3.5. So it really is a lot more reliable. So after you crank through all this, here's your like a z-score, and look at this, 42. Imagine something 42 standard deviations away. So obviously 3 is greater than, or 3 is less than 42.33, but it shows you how far out of sync it is, how far out. Box plots, calculate the quartiles, 25th, 50th, 70th, 75th percentiles. The interquartile range is subtracting the 25th from the 75th, and that's the middle 50% of the data. There's a distance here. Here's the mean. Here's the 25%. Here's the 75%. You take this measure, like using k equals 2 or 3 in the previous methods. 1.5 is a very standard thing that is used. It goes back to Tukey, I think. And the implementations of this are going to give you that. You can modify it. But anyway, box, these are the whiskers. And the boundary between inliers and outliers is 1.5 IRQs on either side. So we have, in this case, whatever this data set was, we had 4 up here and 2 down here. And this is the way it's drawn by the software. Very interesting. So in this example, we crank through all the numbers. Look at this. The whisker way down there, this thing is way, 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 way out there. Again, these methods are showing you how far this really is. The important thing about these last 2 methods, especially this one, is they're not non-parametric, meaning they don't assume anything about the data. They don't assume it's normal. When you use a z-score, you are essentially saying this is normally distributed. And when it's not, it doesn't work as well. Now, lots of data is normally distributed, but you'd have to be careful about that. You'd have to think about that when you look at a piece of data. Is the feature normally distributed? That might affect which method you use. Okay, here's some data with a normally distributed, and some of these ended way out here. Mean, first, second, third, standard deviation. So standard z-score, if we set the boundary at 3, obviously these are outliers. 1.92% of the data. Remember that when you're using the z-score, you say, oh, well, it's going to be 0.23% of the data with 3 standard deviations, only if it's normally distributed. It'll be less accurate. And we can see here it worked, not too bad. Robust z-scores, much more aggressive. Look at this. It is responding to the idea that there's a clump. There's a huge clump in the middle, and the things that are in the sparse, suburbs are regarded as outliers. So it's making a different kind of a decision. If you have normally distributed data, then sure, you can use the z-scores. Box plots again, or work with median and percentiles. Here's the median, first, second percentile. Here are the whiskers, and so you've got 3 out and 2 in. Here we go. This is what you'd see. It doesn't list the numbers, but you can see what's going on. Okay, let's talk about how you would extend this to multivariate. When you have a multivariate data set, what that means is that it's a matrix. So here are your samples. Here are your entries in the data set, and these are the features. Okay, so you have p features, n samples. But if you just consider one of these columns, it's of course one-dimensional. And this is called a marginal distribution. If you just consider one column or one in general, one piece of it, a row or column, and you make some argument about that. You look at the distribution, but it's called a marginal distribution. So sometimes these are called marginal methods. Coordinate-wise is a little more descriptive. So basically, for each of the columns, you go through and you pick a one-dimensional method, apply it to the first column, forget about the others, then apply it to the next column. Now, that means somewhere in this matrix, you're going to identify some outliers. You're going to cut every sample out that has an outlier in it. You could also have other rules, right? You could say, oh, if there's more than 3 or something. But in general, you're identifying the places in this matrix that are outliers, and you have to decide what to do about the samples. Or maybe the features. Sometimes we remove features from a data set if it's corrupted. Lots of ideas here. But anyway, you're going to find out where the outliers are without dealing with any relationship between any of the dimensions. It's very easy to do. It works fine. This kind of thing, this coordinate-wise method works fine if for a very simple situation, which I talked about above, where if somebody makes a mistake or there's a sensor that goes bad or just some feature got corrupted, it'll find it very easily. But there are limitations, and that is that they ignore correlations. So when your data has independent features, then these methods will work okay. But when there are correlations, for example, kind of a silly example, female basketball player, she's 6 feet tall, but only 120 pounds. Seriously skinny. This may not be an outlier. This may not be an outlier, but together, that is highly unusual. So you have to be able to account for this. You have to be able to understand the data with relationships between the pieces. So the true multivariate outlier detection, and there's a lot of these, but the simplest one is called Mahalanobis. And the correct multivariate generalization of the z-score is to account for the correlations between features. If it's independent, you can use many of these methods naive methods. But when it's not independent, it doesn't work so well, like the basketball player. So let me show you an example. There's a covariance matrix, and that is you take the expected, well, it's the relationship between these two features. And basically, do they vary together? They'll have a high covariance. Do they vary opposite each other? Then they have negative. Or are they independent? Then it's 0. When you take the covariance matrix, so here's an example of a covariance matrix. When you normalize it, standardize it by dividing by the standard deviation of both of the features, you get the correlation matrix. And that gives you the correlation between the features. And it leads, when you do a heat map of the correlations, that's what's showing. But here's the thing you really have to think about. Suppose I take a standard normal, 0. I chose X and Y. Well, most of them are going to be in the center, and then any way you go out of this, it looks like it just decreases in a normal distribution. It's symmetric in every possible way here. So they're independent. And if you think of a boundary from 0, some distance from 0, it would be a circle, right? So you have a series of circles that determine, where the cutoff is. And you might follow some distribution and how that circle changes and so forth, or where you set it. But when you have correlations between the features, then you have something like this. So what I did was I took this, I multiplied it by this covariance matrix, and it did this. I literally took the points and multiplied the matrices together. That means you take this, multiply it by sigma, you get this. Okay, but these matrices they're symmetric. They're always invertible. So if I have a correlated data set, I can send it back the other way and make it uncorrelated. I can remove correlations. So the gold standard, the way to really do this, consider points to be, points in a vector space with relationship to other points or other vectors. We're going to use this notion of distance, where basically this is a little bit complicated, but what this says is I'm going to take this normalized value, this vector, and I'm going to send it back this way, and then this normalize it at the other end. But anyway, you're going to take your data and uncorrelate it, and then you will take the square root. So it's like if you do this one, you could say it's Euclidean distance, right, from the center. Here you're going to send it back the other way and then use Euclidean distance, essentially, like the square root. And so that's the basic idea. You're going to use this metric that's defined in a certain way that accounts for the shape of the data, because otherwise you're basically saying everything is sort of spherical, right? It's just not true. So you square this, and then there's one more thing. You have to use the chi-squared distribution, which is a distribution that tells you the relationship between two vectors. And it gives you a way to compare two vectors. It has better properties than somehow using the z-scores or average of z-scores. And it has a distribution. I think I showed it below. And basically, instead of the normal distribution curve, there's a different distribution you use that's mathematically appropriate. You're going to choose these cutoffs. This is more or less 99%, more or less, you're expecting it to be about this percentage is in the boundary and this is out. It's not exactly corresponding to 3 sigma and 2 sigma. Not exactly. But anyway, these establish a cutoff like you had with the univariate methods. Once you do this, so it's the genuine multivariate analog of a univariate z-score because it accounts for the shape of the data. And it's the best way to do it. But let me show you. Here, let me create a 2D data set. I added 5 outliers, just threw them in there. You can see there's going to be some problems here. Coordinate-wise, it just flags something. If one of the dimensions, this way or this way, is too far away. You see it picked up this one, grabbed all the other ones. This is for 3 standard deviations. With our new method, I set this to, let me set it back to, let me set it to 99, which is what we had up there. And yeah, it picked up the same ones. It did the exact same thing. Of course, now, like with the other one, the others, you can set this to a different number and it will pick up more outliers. Yeah, it grabbed these 2 now. I guess that's most. Oh, and it grabbed this one. So this is the gold standard. You can read through this if you'd like about why it works. But basically, instead of some sort of circular boundary with some curve that tells you where the cutoffs are, now you have ellipses or hyper-ellipsoids in multiple dimensions. But basically, that's what it's doing. Instead of a circle, it's pulling it out and making it into an ellipse. Okay, there's a bunch of other methods that are worthwhile thinking about, maybe going forward. Density-based methods, isolation, these are based on decision trees. Density is like we saw that one method, it understood that the density was in the center, and where it was very sparse, it found the Outliers. A very interesting idea that you'll see again in Mod 7 is an autoencoder. An autoencoder is a neural network. It takes an image or whatever, and it sends it through a bottleneck with a limited amount of space. And it needs to compress, it's like image compression. And it needs to figure out what the relationships in the data are so it can compress it adequately. Well, outliers are harder to compress. So this gives you another metric. You measure the loss. How well can you reproduce an image? And it's very interesting. It's hard to compare with these because it's mostly used on things like images. But anyway, good luck. I'll stop here.